Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Let's continue with more hands-on session exercises today. In this class, we will focus on a template called phase diagram template. This is different from the binary template that we have used in the last class. And using that, we will plot binary phase diagram and metastable binary phase diagrams. This is going to be interesting. Then we will see ternary template and plot ternary phase diagram. Okay, so this is going to be our exercise today. FECR phase diagram using phase diagram template and not binary template. Okay, what is the difference here? A binary template is only for binary systems, whereas phase diagram template is a generic one. Multi-component phase diagrams also we can make using this phase diagram template. Right now we will do the similar exercise that we have done in the last class, but the exercise here to make use of this phase diagram template. That's the reason why we are doing this. So it's not a repetition, it's a slightly different one. To do that in Thermocalc software, use graphical mode with the new project, select template phase diagram. Okay, in that we will have again these three different stages. So we have to select the database FE demo, select element FECR, not much change in that. In the equilibrium calculator, we have to set two axis definition. So in a phase diagram template, this is what we get. We get to choose two different axes. And for the first axis, we are going to choose temperature 298 to 2200. And for second axis, we are going to choose composition of chromium from 0 to 100. Then we can visualize the phase diagram. Let's do that. Okay, we are in the graphical user mode now, and you can see here the phase diagram template is here. Yesterday we used this binary template here. Today we will use this phase diagram template. Click on that. Okay, FE demo database, select elements FE and CR. FE first, CR next. Then go to equilibrium calculator. We get to choose two different axis definitions. You can see mass percent of chromium, temperature, both are here. Mass percent 0 to 100 is already there, will not disturb that. And temperature will start from 298 to 2200. Okay, so two axes we have set. Here nothing need to be changed. We can directly go for perform tree. Click perform tree. Right, so now the calculation is over. Okay. So now we got the phase diagram. You know how to adjust this and export the results. Let's go back and do the next exercise. Okay, so we will now see how to do metastable calculations. For that we need to choose this system, iron carbon system, and calculate the iron cementite phase diagram. You see, generally iron carbon diagram is iron cementite diagram. People, industries in different metallurgy labs and all, you will see that iron carbon diagram is hanging. People call it iron carbon diagram. It is actually iron cementite diagram. Okay, I will show shortly how does it look, and that's what we want to make. Clear knowledge is this: cementite is practically stable, although thermodynamically only metastable. Practically stable in the sense it can be stable for millennia. Cementite can be there in the material with iron and carbon. If you make a material, especially the mild steel and all, there will be cementite in that. Cementite is Fe3C, it's an intermetallic compound, and that compound is going to be practically stable. But that's not the most stable form for carbon to be in. Carbon actually wants to become graphite. Okay, that is the most stable state. But if it is in the cementite form, then we are going to call it as metastable. Okay, so we are going to make iron cementite phase diagram, we are going to call it as metastable phase diagram. Okay. So to do that, this is what we need to do in the software. We are going to use the phase diagram template in a new project, and we are going to define FE demo database, and so defining iron and carbon as our elements, and then temperature range is going to be this, and the composition is going to be carbon 0 to 100. Okay, and in plot renderer we can set the x-axis up to 7 mass percent of carbon, because cementite appears at 6.67 mass percent carbon. In fact, the widely used iron carbon diagram, which is actually iron cemented diagram, will have carbon content only up to 6.67. It will not be up to 100% carbon. Okay, let's see how to do that. Before that, let me show, if I simply in Google Images, if I simply search iron carbon phase diagram, FEC phase diagram, this is what appears. If I click on any random diagram, let's say like this is what I see, and you can see up to 6.67 percentage of carbon is what the diagram is drawn, and that's where Fe3C intermetallic phase stands. It's a line compound. Okay, forget about all the other details here. I want you to focus on this x-axis. It's plotted up to 6.67%, and it is called as iron carbon phase diagram. This is how generally it is done, but this is not iron carbon phase diagram, is iron cementite phase diagram. Okay, because it is drawn between pure iron and the cementite phase. Although carbon is changing in x-axis, this is not strictly iron carbon phase diagram. Okay, let's see how to make that in the software. Okay, we're going to use the phase diagram template. Click on that. Right, we got the system definer stage now. FE demo database is fine. We're going to click on FE first and carbon second. Iron and carbon, select those two elements. Job done at this stage. Go to second stage, equilibrium calculator, where we are going to change two variables, two axis definitions. We are going to give mass percent of carbon 0 to 100 is there. Let's leave it there. And temperature we will keep from 298 till 2200. Okay, then click perform tree. Okay, now we got the result. So tie lines are there. We can remove that using plot renderer. Legend option is off. Then click perform. Now we got this diagram. Let's make x-axis from 0 to 7 mass percent carbon. Okay, so right now x-axis is now carbon mass percent. Automatic scaling is selected. Uncheck that. Then here limit 0 to 7. 0 to 7. Then click perform. Okay, now we got this diagram. We'll just try to label near the 7%. Okay, so x-axis, let me also 0 to 7 steps of 10 is given. Let's take this 10 to 1 so that we will see x-axis clearly. Okay, so what I'm doing is one more change in the x-axis. Next to this step I'm putting number 1 and then click perform. Okay, now you can see 0 to 7 at steps of 1 appear here. So near 7, somewhere here, If I right click and add label, I should see cementite if it is a metastable diagram, but what I see is BCC plus graphite. Okay, BCC plus graphite here, and here if I see FCC plus graphite, okay, and at a higher temperature it is liquid plus graphite. Okay, meaning graphite appears if I try to add carbon to iron. What happens is, you can see in the left extreme, I'm trying to zoom in to this area, so just click the mouse and drag it like this and leave it. Then you can see only up to, let's say here, if I keep the mouse, you can see 0.2. Okay, 0.2 is there in the brackets, meaning that's the maximum carbon content up to which I have zoomed into. Okay, in that way you can see here BCCA2 appears here. This is the iron in BCC structure, and maximum carbon that you can add is only this much. Beyond that, if you add, you enter into BCC plus graphite region. Okay, so only up to here you can see 0.016 or so, 17, that is the maximum amount of carbon that can be added to BCC iron. That's how it comes in this database. Okay, so if you add anything more, graphite is going to come out as a second phase. And if you want to go back and see the original diagram, click anywhere in the diagram and drag to the left top like this. Okay, so for your understanding, I'm going to do it again. So if you want to zoom into any area, just click somewhere and then put a small box like this for whatever composition is of your interest and leave it. And now you see the diagram in that selected zone. If you want to go back, click anywhere in the diagram and drag to the left top and leave it. Okay, right. So now you got this there. At a high temperature, you can see FCC iron can accommodate more carbon, up to even 1.92% carbon can dissolve in FCC iron. So that's how FCC can accommodate carbon. But if you add anything beyond that, if you cross this black line here, if you cross this, you get into graphite plus FCC region, meaning any more amount of carbon will give two phases. Graphite will be one of those phases. Now you get the point. So we see graphite as the stable phase here in this diagram, but we want cementite to appear at 6.67% carbon. So let's see how to do that. Okay, so this is what has happened. Graphite appears, cementite doesn't. So what we are going to do is remove graphite from calculation and try. So to do that, this is what we are going to do. Right click on system definer of example of exercise 10 and clone tree, and then in system definer stage, do one change, unselect phase graphite, and repeat everything similar to the previous exercise. Let's do that. Okay, so we're going to right click on system definer and clone tree. Okay, so now we got a cloned tree here, and in system definer we are going to make a change. What we are going to do is remove the most stable phase, that is graphite. Okay, so click on this third tab, phases and phase constitution. In that, remove only one phase, graphite. This graphite can be removed. Okay, so uncheck graphite, everything else is going to be same, so we can directly click on perform tree. Since we have removed the most stable phase, graphite, whatever diagram we are going to get now should be called as metastable diagram. But let's see whether we get cementite at 6.67 as a line compound. Okay, so we got the diagram here. These labels are coming from the previous tree because the tree is cloned. So our first job is to delete these things. Just click on this label and click delete. Click on each one of them and click delete. Okay, now we can right click and see what phases are there. Add label. You see, if I click in the bottom, BCC plus diamond FCCA4, those are the phases appearing. So in this domain, these two phases are there, BCC plus diamond. Okay, this is diamond structure for carbon. If graphite is removed, diamond becomes stable, not Fe3C. But at high temperature, we see cementite coming. Okay, BCC plus cementite, and here also BCC cementite is there along with FCC. So we are getting at 6.67. You can see I am hovering my mouse here near 6.67. I see a line compound cementite, but it does not appear at lower temperatures. It should appear at lower temperatures also. That's how the iron cementite diagram looks. So let us see how to bring that. What happens if we remove diamond also? Okay, shall we check that? So graphite appears. Now what happened is diamond appears, cementite doesn't fully appear. So remove diamond from calculation and try. Okay, so let's try that. To do that, we are going to do this change now. So everything else is going to remain the same. We are going to clone the tree from the previous exercise and unselect phase graphite, which is already unselected. We are going to unselect diamond as well. Okay, we are going to do that. Let's see that. Okay, so right click on system definer, clone tree. Okay, again go to system definer, in the top system definer 3 now, and in that go to third tab, phases and phase constitution, and remove diamond. This is here, diamond FCCA4, remove that. Okay, then click the bottom, perform tree. Okay, so now we can see how is the diagram. Okay, so you can see first of all you remove the labels from the previous tree, delete the labels, delete, and y-axis starts actually from 298 Kelvin. So this line actually starts from 298, which is the calculation we have done. So that is a line compound cementite that is appearing here, BCCA2 plus cementite. Okay, then here again cementite plus FCC, and at high temperature liquid plus cementite. So all of them are appearing with cementite. So cementite is there stable up to melting point from room temperature. So this is the diagram we have been looking for, and this is the one which is industrially very relevant diagram, and this is how you get the metastable calculation done. Okay, now required iron cementite phase diagram appears. Now let's try the ternary phase diagram using ternary template. There is a dedicated template to make the ternary phase diagram. Of course, phase diagram template, the one which you have just used, can also be used to make ternary phase diagram. We will do that later. First, we will try the ternary template itself. Okay, so this is the exercise we are going to do. FeCrNi, iron chromium nickel isothermal section of phase diagram at 1200 Kelvin. We are going to make that, and this is the procedure in the software. We are going to use a graphical mode with the template ternary, and in project window we are going to see two stages just like the binary template. Here ternary calculated appears, where we select database, FE demo, select elements FeCrNi, and select temperature 1200 Kelvin and perform tree. Okay, then in plot renderer we can visualize the diagram, and we can remove tie lines and change the legends if we want. I'm going to click on new project. You're not saving this old project. And the templates, select ternary. Click FECRNI. Okay, 3 elements we have checked. FE demo database is chosen by default. That's okay for us. And isothermal section at temperature of 1200 Kelvin is what we are looking for. You can type 1200. That's all. Then click perform tree. Okay, now we got a diagram and we can remove the tie lines. Tie lines make it 0 and legend option stable phases. Switch it off. Then click perform again. You get a nice clean phase diagram. You can see here different regions. You can right click and label region names FCCA1, BCCA2, and in between you are going to get all two phase regions. There is one single phase here, sigma. Okay, and we have these two phase regions BCC plus FCC, here sigma plus FCC, here BCC plus FCC again, here sigma plus BCC, and these tie triangles are here where three phases coexist, BCC, sigma and FCC, here BCC, sigma and FCC, right? So we got the, I just labeled only the single phases. Now we got the ternary phase diagram, right? So it shows the phase diagram with tie lines. Tie lines and legends can be removed. We have done that. Right click and add label. If you click show details, you can see the results of single point, just like in the binary phase diagram. So at any point you can click. If I click in this tie triangle, right click and add label, and here if I click show details, I will see, I can drag down and see stable phases. BCCA2 is one stable phase, FCCA1 is the another stable phase, and sigma is the third stable phase. So three phases are there within the tie triangle, and their individual compositions can be seen here in mole fraction and mass fraction. Their volume fraction, individual phase volume fraction is also given here. So one can get such information. Okay, right. So now we can ask some interesting questions from the diagram. Among single phases, which are extended unary phases or extended binary phases into ternary regime? Okay. Is there any ternary emergent phase? Is sigma not an extended binary phase? Because it looked like it is in the middle of the diagram. Is it not an extended phase? Is it an emergent phase? Now to understand that better, we have to check the ternary isothermal section at 1000 Kelvin. Okay, just to answer this question, let's try to do that. Okay, so to do that diagram at 1000 Kelvin, we can do a right click on system definer in the previous example and clone tree, and project window shows a tree of two steps, ternary calculator. So let's do the entire thing again at 1000 Kelvin. Ternary calculator, in the ternary calculator, right click, clone tree, okay. So here we have ternary calculator 2 and plot renderer 2. We are going to make one change in the ternary calculator, that is change the temperature from 1200 to 1000. Okay, and then click perform. So now the diagram is here. So the labels you have made in the previous things are up, previous tree are appearing here. We can delete them. FCC is still okay. You can, if you right click here and add label, you will see FCC. So it's fine. Sigma is also fine actually. This is the sigma phase. You can see sigma starts from the binary side and gets extended into the ternary regime. You see, entire region, this is sigma region. But at 1200 Kelvin, we see only a sliver of sigma coming. This sliver is actually stable. I mean, more nickel containing region this is. This sigma is stable at 1200 actually. If I click on plot renderer 1, you can see sigma is like an island within the ternary regime, not coming extending from the binary side. It's because this is a section at 1200 where the sigma phase is like the ternary phase alone. It's looking like a ternary emergent phase, but it is basically stemming from the binary as we see at 1000. Okay. So if we make a vertical section, temperature as one axis, we will try to do that in the future classes. Across this sigma phase line, you will see that at 1200, the sigma phase is extending from the left hand side of the diagram. Let's say if this is where the diagram starts, we will see the sigma phase going from here to here, whereas at 1200 it will not be starting from the binary side. Anyway, if it is confusing now, wait for the vertical section classes. We'll do that. Okay, so now here single phase BCC is somewhere here. Okay, BCC region is very small at 1200. You can zoom into this area, right click here, add label, that is single BCC. Okay, then click anywhere and drag to the left. You can see BCC here. If I move it here, you can see this small region here is the BCC region. Right. So sigma phase is an extended phase, is an extended binary phase. You know, in binary level it was an emergent phase. That emergent phase is now extending into ternary regime, meaning FECR accommodates nickel to that and becoming a phase in the ternary regime. But it is actually an extended binary phase. Now we will make the same phase diagram, ternary diagram, using phase diagram template. Okay, not the ternary template, phase diagram template we will use. For that we need to choose the template phase diagram, and then 3 steps will appear, and we have to define the axis now. Okay, the database remains the same. Select element FECRNI, 3 elements, but in equilibrium calculator we will see 2 axis definitions possible. We are going to define both of them to be compositions, one for chromium, one for nickel. Iron is going to be dependent. Third element composition value will be dependent. Okay, then in plot renderer we have to toggle to triangular type so that we can see that typical ternary isothermal section kind of thing. Otherwise we will see a rectangular diagram. Okay, so let's see how to do that. This module is important to learn because this is where even multi-component diagrams or vertical sections are possible. So let's do that. Let's go to new project, not saving the old one. Let's go to phase diagram template, this one. Okay, so FE demo database is fine. I'm going to select FE first, that's going to be dependent, then CR, then NI. Okay, 3 elements are selected. Then go to equilibrium calculator, and in the bottom you have to select 2 composition values. Mass percent of nickel is already there, 0 to 100, that's fine. Second axis definition is going to be mass percent of chromium. Okay, that also should go to 0 to 100. So now we have defined 2 axes. Okay, now click on perform tree. You see what appears is a rectangular diagram. Mass percent of nickel, mass percent of chromium in 2 axes. So if you want to change it to a typical ternary diagram, go to plot renderer, and in the top you see configuration, and the second one, look, triangular symbol is given, toggle triangular to rectangular type. So click on that, then click perform in the bottom. Okay, now you get the ternary phase diagram that we wanted. Okay, here chromium is here in this axis, nickel is in this axis, tie lines are there. Looks slightly different from what we got in the ternary template. You can change that here. X-axis composition, nickel is there right now, you can change it to chromium, and y-axis chromium is there, you can change it to nickel. And tie lines you can remove, make it 0. Legend option you can switch it off, and then click perform. You will get a diagram that we got in the previous step. Okay, so this is at the 1000 Kelvin. So now we have used the phase diagram template and plotted the ternary diagram. In the next class also, we will see phase diagram template and try to plot more diagrams such as vertical sections. Eventually, we will see that there are limitations to this. In fact, there are limitations to the graphical user mode itself. So we'll try to go to console mode and do some exercises which are more complex in nature. And eventually, we'll come back also to graphical mode for more simpler calculations later. Okay, thank you. I hope the lecture is useful. See you in the next class.